Okay guys, I just want to give you a quick visual that might help yesterday's or the previous lesson make a little bit more sense to you. I have a pair of special glasses over the lens of my camera right now aimed at a light on my desk, and you can see that it's taking the light, that white light, and splitting it up into all the colors of the rainbow. All those different colors of the rainbow have different amounts of energy, and we're going to look at those, talk about those a little bit in class today. So those glasses are special, whereas they take the white light and they take all the electron jumps that are occurring, from the ground state to the excited state and then back down to the ground state. It's splitting those up into the different energy levels that they have, or different energy amounts that they have. And the different energy amounts coincide with a different color of light on our visible spectrum. So you can see when I take the glasses away, that's what our eyes normally see. Our eyes don't have the ability to split the light into those different colors. But when I put the glasses back, you can see that it splits the light into those different energy values or levels, and we can see through those glasses what those levels are. Now if you take an element and you heat an element up, and I'll show you a flame test demo in a few minutes here, you're going to see only specific energy jumps. So you saw that on some of the slides yesterday. So you saw a couple different elements with a limited spectrum of colors, because different elements have different electron jumps that occur from ground to excited and then back down to the ground state. Those different electron jumps in different elements help us identify what those elements are. So you can take a look at the spectra for sodium, for example, or barium or copper, and then that's what we can use as like a fingerprint to identify what that element is. So if you have an unknown element and you look at the spectra that it creates, you can compare it to the spectra that we know of and see which one it matches up with, see what element it matches up with, and we could figure out what that identity is. That's how they identify different gases that are in stars or some other components of some unknowns. Okay, so I hope that makes a little bit more sense to you guys, and we'll take a look at some demos here in a few minutes.
You shake my nerves and you rattle my brain. Too much love drives a man insane. You broke my will, but what a thrill. Goodness gracious, great balls of fire.
Alright guys, I don't even want to talk about how long it took me to make that ridiculous video you just saw, but one of my favorite labs in this course is the flame test lab, and unfortunately I don't think we're going to get a chance to do that this year, which is really disappointing. It's one of the labs that students usually really remember, and they like to take a lot of really neat pictures and record some different things, and it's just really cool. So that was my attempt at letting you guys see what that lab was all about. So I was a little disappointed at the end of the video because the flame colors didn't show up that well, because it was really hard to film in my basement. But I had those 4 different compounds there, and all of them had a different metal, a different cation in the beginning. And you can see that when I added the ethanol, which is flammable, and the ethanol burned along with the compound that was dissolved in it, you can see some different colors of the flames. My favorite one is copper, and I also like strontium. It's like a neat red color, and it was a little bit hard to see that in the video. But that just goes to show again that every element has its own unique spectra. So the electron jumps in copper give off a green color of light, and all the electron jumps in strontium give off like a reddish, really neat red color with that light. And the other ones that were kind of hard to see, cobalt gives it's like a sparkler, like a 4th of July sparkler you might use. So that was pretty cool. And the other one was barium, I believe, and barium should be a neat yellow color. A little bit harder to see that on there. But anyway, that just gives you guys a little bit of a glimpse of what the flame test lab was all about that we're going to miss, and what those look like. You can see the image on the screen here. It gives you a little bit more of a better idea of what some of those look like if it was a really pitch black in the room and you had a better camera to see what those colors were. Okay, so anyway, moving on. Alright guys, so I have this picture here because you should be able to see really 2 images within the one image. So if you take a look at it, you might see one of 2 images primarily, or first. The one that I usually see first is the old lady. But some other people look at this and they see a young lady. So if you're having a hard time visualizing it, the old lady is here. There's her nose and there's her mouth. And if you see the young lady, or if you can't find her nose is right here, eyelashes, it's her hair. She's wearing some sort of like scarfy thing, and there's her chin down here. So why am I showing you this picture? I'm showing you this picture because you see 2 things in one picture, 2 things in one. What we're going to look at is the dual nature of light and electrons. So electrons are interesting because they act like matter, which are particles, and they also act like energy, waves. So they're just electrons, right? But they act like two things at the same time, matter and energy. Now, usually we think of matter and energy as two separate entities or two separate things. But when it comes to electrons, and we're looking at the nanoscopic level of everything here, they act like particles and like waves. So we're going to look at some of those characteristics today, some properties of a wave, and we're going to look at how we do some calculations with those. So at the atomic level, like I said, the distinction is blurred, and matter has wave-like properties, and energy exhibits matter-like properties. So electrons are what we really focus on when we're talking about this. So a couple definitions for you on your, or in your packet, I should say. One of them is wavelength, and that's the Greek letter lambda. It's the distance it takes to go through one complete cycle. So you have a picture of a wave on your note sheet, and you can label what the wavelength looks like there and write the definition in. The common unit for a wavelength, is a nanometer. Okay, so let me write some of this on here. All right, we'll just do this. So a nanometer. So it's a unit of length. Okay. Same thing for amplitude. It's the vertical distance from the middle to the peak or trough of a wave. It's also a unit of length, so we're going to look at a nanometer there as well. Another unit of length we can use is an angstrom. Okay, so you might see it as an angstrom, you might see it as a nanometer. Either way, both of those are a unit of length. And we talked about angstroms earlier in the unit when we talked about the size or diameter of an atom. So the wavelength and amplitude of this wave, you can take a look at it and try to figure out what the wavelength is and what the amplitude is. I'll give you a second to do that. Okay, so hopefully you got those right. The wavelength is, let's see my pointers here, the wavelength from here to here. So that's 10, 11, it's like 13, and I don't know what the unit of length is here. 13 nanometers or angstroms, I don't know. And the amplitude is from here to here, so it looks like 1. So pretty simple. All right, another term, frequency. And that's like a cursive V, if you're trying to write that, that Greek letter there. It's the amount of cycles the wave goes through per unit of time. So it's easier if I was actually in class to show you a quick demo of this, but it's kind of like how fast the wave is moving. So how many times does the wave pass a point in time, or a point per unit time? So how many cycles does the wave go through, like every second? That's actually what the unit is. So the unit is really 3 different ways to write this. 1 per second, because it's per second, okay? Another way to write that is seconds to the negative first, and another unit that represents per second or seconds to the negative first, and that is hertz. Hertz, right there. Okay, so those are your 3 units of frequency, so we should know what those are. Okay, you have a couple of relationships between frequency and wavelength, and again between frequency and energy. So we're going to look at these 2 equations. No need to memorize these, they will be given to you, but we have C equals lambda, and that Greek letter for frequency is nu. C equals lambda nu. What does C stand for? Well, C stands for the speed of light, and that's 2.998, or usually just round up to 3 meters per second. So this gives us the relationship between wavelength and frequency. If you notice, the units on C are meters per second. If you take lambda, which we said was a nanometers or angstroms, or another unit of length, which is meters, times frequency, which was 1 per second, and you do the math, you get meters per second. Oops, that was horrible. Sorry. Okay, so that's what you get for the unit of speed of light, which makes perfect sense. So what you can do is plug some values into lambda and nu, and solve for your unknown. Easy. If you look at the relationship between wavelength and energy, it's interesting. Spend a little bit of time talking about this. Shorter wavelengths, like gamma rays and X-rays, have high amounts of energy. Longer wavelengths have low amounts of energy. So you can see the electromagnetic spectrum here. Gamma rays, look how small that wavelength is. 10 to the negative 14th nanometers. That's our unit here. And then radio waves, FM, AM radio waves are pretty big. I mean, that's huge, 10 to the 4th meters. It's a really long, big wave. All those colors of light we saw on the earlier parts of this video, that's part of our visible spectrum. So that's right here. So our visible spectrum is only a wavelength between 400 and 800 nanometers. Any wave that has a wavelength of less than 400 nanometers, we can't see any light associated with that. Like if you go to the doctor and get an x-ray, you can't see that. But obviously we know it's there. So they put that lead apron over you. And any wave that's longer than 700-800 nanometers, we can't see either. Like you can't see your radio waves when you turn the radio on in your car, right? Can't see those. We can only see the ones between 4 and like 700-800 nanometers. The dangerous radiation is ionizing radiation, and that's when we have a shorter wavelength, which is again why the dentist or the doctor will put a lead apron over part of you if you're getting an x-ray taken. I spent a little tiny bit of time on this just so you know why radiation can be so bad. The ionizing radiation is the bad radiation because it creates something called a free radical, which is basically a really, really mad atom. So you have Cl2 and then go through some sort of ionizing radiation and it breaks it apart and you basically lose an electron. Okay, so you have an unstable atom because it lost an electron, an unpaired electron right there. And it just makes it really mad. And when it gets really mad, it can cause damage to tissue, which is in your body, obviously, and it can cause, possibly cause cancer if you have those cells, the damaged cells, making more damaged cells, right? So that's the danger of ionizing radiation. Non-ionizing radiation obviously wouldn't do that. Okay, one last equation and relationship here between wavelength and energy. So E equals h times nu. H is a new variable. It's a constant. It's called Planck's constant. So it's 6.626 times 10 to the negative 4th joules times seconds. So that's the unit on that. So if you look at energy, energy is in joules. Your Planck's constant is in joules times seconds, and your frequency is in per second. So if you take the units on H, which is joule times second, and you multiply that by 1 over seconds, seconds cancel, and you get joules, which is your unit of energy. Lovely. Okay, so some practice calculations here. If you look at your packet, the next page, if you look at problem number 1, I'm going to flip to it on mine here. If you look at problem number 1, we're going to actually solve that. And I'll show you guys very quickly how these work. So actually, we're going to skip number 1. Number 1 is just a factor label problem because you're going from meters into nanometers. So we're going to skip that. And we're going to go to problem number 3 instead. So let's see if I can find a better pointer here. Let's see. Let's go with that. Okay, so for problem number 3, it says determine the wavelength if the frequency is 8.79. This is going to be a mess. 8.79 times 10 to the 13th per second. Okay, that's the frequency. I want to know what the wavelength is. So we're going to use the first equation, which is C equals lambda times nu. Not bad. Okay, let's reorganize this equation to solve for wavelength, which is lambda. So divide both sides by frequency like this. That goes away. So we have C over frequency equals lambda. Okay, from here on it's easy. Plug in what we have for C. It was 2.998 times 10 to the 8th meters per second over your frequency, which was 8.79 times 10 to the 13th per second. The seconds cancel here, per second, gives you your wavelength. Okay, so we need 3 sig figs in our answer, and you get, do your math right way in your calculator, don't screw that up, and you get 3.41 times 10 to the negative 6th meters. Okay, it doesn't tell you what to put your answer in, it doesn't say meters, nanometers, angstrom, so that is fine. Okay, so that is my wavelength. right there. That is the same as 3410 nanometers. So you could look on the electromagnetic spectrum and see what type of radiation would give off, and it would have the wavelength of that. All right, so that was pretty easy. Number 7 is similar to that. Let's clear this. Okay, so last chance to write that down. Erase all. Okay, there we go. Number 7, it says, what's the frequency of a wave with an energy of 1.12 times 10 to the negative 16th joules? So we're going to use our energy equation. E equals Planck's constant times frequency. I'm given the energy. Okay, so I have my energy there. I have Planck's constant. I always do. So my frequency is unknown. So let's reorganize this and solve for frequency. So we would get E over Planck's constant equals frequency. And we plug our numbers in. Okay, so we have 1.12, 1.12, that's a 2, and that's a times 10 to the negative 34th joules times seconds. I'm sorry the clicking is so annoying, but we will live. Over Planck's constant, 6.626 times 10. Oh, I totally screwed this up. That is to the negative 16th. Oh my goodness. Okay, times 10 to the negative 34th. Okay, now we're back on track. Joules per second, and that was just joules. This is a disaster. Okay, now this is joules times seconds. Okay, joules cancel. Fantastic. Our unit would be 1 over seconds, which it should be for frequency. So we're back on track here. And we need 3 sig figs, so we get 1.69 times 10 to the 17th. That's pretty normal. Frequencies are pretty fast. That's a lot of waves per cycle. That's a lot. Okay. Per second. Or hertz is equal to your frequency. Okay, so easy money, right? Now, you have other practice problems, so I did 2 of them for you, so you don't really have that much left to go here. They're not that hard. Some of the problems, like number 8 and 9. Number 8 and 9, you guys have to use both equations. So you might have to solve for like frequency first in one equation, and then plug it into the other equation and solve for wavelength, or going back the other way. All right, so the thing that's consistent in both equations is frequency. That's our link. All right, so again, you might have to do 2 equations here, like solve one first and then the other one. So anyway, take some time and work through the next 2 pages in your packet. So questions 1 through 9. We already did number 3 and 7. And then you can check your answers with the answer key folder, and it'll be clear on the roadmap or in the lesson plans how to check your homework or how we're going to check that as a class. So anyway, hope you guys found this relatively straightforward and interesting. This is actually the end of Unit 7. We'll figure out how Unit 8 is going to go and what that's all about in the next couple days. All right, guys? Sounds good. See you later.